Welcome to the deep dive. Today we're jumping into something really fascinating, a Nobel Prize-winning area of physics.
That's right. We're talking topological phase transitions.
Exactly. A concept that really, well, it turned a lot of established physics on its head, thinking about the work of Thouless, Kosterlitz, Haldane. Amazing stuff.
Absolutely. And for you, maybe you're a physics student listening, our mission here is to sort of unpack how these really strange phase transitions happen, especially in two dimensions, right? Where everyone thought, nope, can't happen.
Yeah, the impossible problem.
It's a fantastic case study, really, in how theoretical ideas, sometimes coming from way out of left field, get confirmed by hard experiments. It's about questioning assumptions.
Okay, so let's set the scene. Early 1970s, what was the standard thinking?
Well, the established wisdom, backed by theorems like Pearsall's argument, Merman-Wagner,
Right.
it basically said that in 2D systems, like a really thin film, almost flat, you couldn't get true long-range order at any non-zero temperature.
Why not? What was the reasoning?
It boiled down to fluctuations. In 2D, thermal wiggles, they just keep building up over distance. Think of atoms in a 2D crystal, they jiggle, and those deviations grow logarithmically with the size of the system. Destroys any perfect long-range pattern.
So no perfect crystal lattice across the whole sheet.
Exactly. Or for something like a 2D Heisenberg magnet, the energy barrier to flip things around and mess up the order was just too small.
Yeah.
No stable ordered state possible.
Okay, so conventional wisdom says no long-range order, therefore no phase transition to an ordered state. Seems locked down.
It really did.
Then along comes Kosterlitz, and apparently it wasn't even his main focus initially.
Right. He was at Birmingham, kind of fed up with high-energy physics, actually. And David Thouless, who was just brilliant, introduced him to these, well, at the time, quite novel ideas. Topology.
The math of shapes that don't change when you stretch them.
Sort of, yeah.
Yeah.
That and things like vortices and superfluids, dislocations in crystals, these localized defects.
And Kosterlitz himself said his ignorance helped.
He did. He suggested that not being steeped in why it was supposedly impossible sometimes let him just try things. A great lesson there, maybe.
Definitely. So what was the big breakthrough idea?
He was realizing there could be a different kind of order. Not the perfect long-range alignment, but something more subtle. Topological order. This order is related to the presence and behavior of these topological defects, like the vortices or dislocations we mentioned.
How does that work? How can defects create order?
Think about the 2D planar rotor model, like tiny compass needles on a plane. They have a topological property, how many full two-turns the angle makes if you go in a loop. Changing that number, creating or destroying a vortex, costs a lot of energy, technically infinite in the ideal model. This creates a huge barrier, stabilizing a type of order.
Unlike the Heisenberg model, where that barrier wasn't there.
Precisely. That topological invariant, that knottedness, allows for a phase transition in the planar model, even in 2D, while the Heisenberg model without it doesn't have one. It's a fundamentally different mechanism.
So this BKT theory, Berezinskii-Kosterlitz-Thouless, it needed a test case. Superfluid helium films.
Perfect test case. Because in these thin films, you get vortices.
Right.
And the crucial insight was that these vortices interact with each other through a logarithmic potential, kind of like positive and negative charges in a 2D plasma.
Okay.
And when Kosterlitz and Thouless applied their renormalization group analysis, a key tool for you physics students to know, they got this inescapable prediction.
Which was?
A universal jump, a sudden, specific drop in the superfluid density right at the critical temperature, TSEA. They even calculated the exact value of that jump relative to TSI.
Universal meaning it should be the same value regardless of the specific material detail.
Exactly, just fundamental constants involved. The prediction was jumping down by an amount proportional to TSA, with the constant being 2-meter TSEA.
Wow. And the experiment.
Bishop and Reppy, 1978. Absolutely stunning confirmation. Their data showed this sharp drop, this jump, matching the theory incredibly well.
Even before they knew the exact number.
Apparently so. The data was there, showing the jump, and then it clicked with the BKT prediction.
Yeah.
It's one of those beautiful moments in physics where theory and experiment just perfectly align.
Incredible. So the theory works for superfluids. Did they apply it elsewhere?
Yes, the next big area was the melting of 2D crystals. How does a flat crystal sheet melt?
Okay.
Kosterlitz initially thought it just melted directly into a regular isotropic liquid. He later called that an unfortunate error.
Uh-oh. What was the correction?
Halperin and Nelson figured it out. They predicted a two-stage process. First, the crystal melts, but not completely. It melts into an intermediate phase called a hexatic fluid.
Exotic.
Yeah, it loses its rigid positional order, but it still retains a kind of six-fold orientational order, like the directions of the bonds between atoms are still somewhat aligned. This happens when pairs of dislocations unbind.
Okay, stage one. Crystal to hexatic fluid via dislocation unbinding. Then what?
Then, at a higher temperature, this hexatic fluid melts into the final, completely disordered isotropic fluid. This second transition happens when different defects, called disclinations, unbind.
Fascinatingly complex. Two steps mediated by different topological defects. Was that confirmed experimentally?
It's harder experimentally. Making good 2D crystals is tricky. But yes, measurements, particularly of things like the elastic properties, the renormalized Young's modulus, show remarkable agreement with the Helper and Nelson theory.
So even with experimental challenges, the core ideas hold up.
They really do. It shows the power of focusing on these topological features. Though some other detailed predictions, like features in the X-ray structure, are still challenging to measure precisely. Physics always has more questions.
Absolutely. So wrapping this up, it's just amazing how looking for these hidden, subtle types of order, challenging that old impossible dogma, really opened up a whole new way of thinking in condensed matter physics.
It really did. And maybe the final thought for you to ponder is this. Kosterlitz's ignorance and these new topological viewpoints unlocked physics that seemed forbidden. So what fundamental ideas or assumptions might we be holding on to today that are perhaps blinding us? What other kinds of subtle order, maybe even more abstract, are just waiting out there to be found by someone, maybe you, looking things a bit differently?